Zeal Education Society, redefining excellence.
Hello, good morning to everyone. Myself Dr. Mahadev Unde, Professor in Electrical Engineering Department, Zeal College of Engineering and Research, Pune. Welcome to my video lecture, Basic Electrical Engineering. In this video lecture, we are going to learn the losses and efficiency of the transformer. Now let us start. What are the losses taking place in the transformer? The types, where they takes place, and the factor on which they depends. Okay, so the losses in the transformer. Okay, there are two types of the losses. Two types. First, copper losses, and the second, iron losses. Iron losses are further divided into ED current losses and second, hysteresis losses. Okay, so let's start the copper losses first. See, the copper losses are also known as variable losses. They depends on load current. Therefore, WCU is directly proportional to I square of the load current, or WCU is proportional to kVA square. Now, if there is no load on the transformer, there will be no copper losses. No copper losses. And these losses takes place because of the winding has resistance, and they are also known as ohmic losses. These losses cannot be minimized. CU losses cannot be minimized. And they takes place in both the winding of the transformer. Therefore, total copper losses equal to I1 square R1 plus I2 square R2 watt, where I1 full load primary current, I2 full load secondary current, R1 primary winding resistance, Vs in ohm, and R2 secondary winding resistance. Okay, now turn to the iron losses. Again, these losses takes place in the core of the transformer. And core is made up of iron material, and hence sometimes it is also called as the core losses. These losses are also known as constant losses because they remains almost constant irrespective of the load on the transformer. Okay, so there are two types: ED current losses say WE. So ED current losses are directly proportional to Bm square F square, where Bm is the maximum fly density in the core and F is the supply frequency. Whereas WH is directly proportional to Bm raised to power 1.6 into F. Okay. So here the ED current losses can be minimized by using laminations for the core construction. Instead of solid core, it is made up of thin laminations about 0.3 mm to 0.5 mm thickness. Okay, and they are varnished in order to insulate from each other. So by using the laminations, CD current loss can be minimized. Then hysteresis loss can be minimized using magnetic material having low area of hysteresis loop. That is say high silicon content steel, for example, silicon content steel. They are also known as constant losses. They takes place for 24 hours in a day, irrespective of load on the transformer. That is, whether the transformer is loaded or not, they takes place for a 24 hours. Okay, also known as core losses. For energy efficient transformer, see, copper losses cannot be minimized. Therefore, in order to increase the efficiency, it is obvious that the iron losses can be minimized. So by using the various good quality of materials, we can reduce this constant losses, that is also known as core losses or the iron losses, and efficiency can be increased. Now say the new title is efficiency of the transformer. Efficiency of the transformer. Efficiency denoted by eta. Okay, so the efficiency equal to output power divided by input power. So this can be written as output power upon output power plus losses, and if it is percentage, you can multiply it by 100. Okay, so efficiency equal to, what is the output power? Phi2I2 cos phi2. This is output power divided by Phi2I2 cos phi2 plus WCU plus WI, and if it is percentage, multiplied it by 100. Okay, so the percentage efficiency equal to, this can be written in terms of kVA into 10 raised to 3 into power factor cos phi divided by, this is say output, so it is kVA into 10 raised to 3 into cos phi, so output power plus WCU plus WI multiplied by 100. So this is the equation to calculate the efficiency of the transformer. So the efficiency of the transformer not only depends on the losses of the transformer, but also on the type of load or power factor of the load, okay. So efficiency varies depending on load on the transformer as well the power factor of the load. So efficiency at any load can be given by so the percentage efficiency equal to x into kVA into 10 raised to 3 into cos phi divided by x into kVA into 10 raised to 3 into cos phi plus, remember this one, x square WCU plus WI. WI is fixed, it is variable, that's why multiplied by x square, where x equal to 1 for 100% load, or we can say full load. Say x equal to 0.5 for 50% of full load. X equal to say 0.75 for 75% of FL. Say x equal to 1.25, so it is 25% overload. X can also be written as x equal to actual kVA load divided by kVA rating of the transformer. For example, say the transformer is 10 kVA, rating of the transformer is 10 kVA, and load on it is not 100%. Say the load on the transformer is only 6 kVA. 6 kVA load. Therefore, x will be 6 divided by 10 equal to 0.6. Or we can say the load on the transformer is 60% of the full load. That is 60% of full load. Okay. Remember one more formula, that is, say the copper losses are variable losses. So WCU at any load equal to WCU full load multiplied by x square or WCU FL equal to WCU at any load divided by x square. Okay, so you can use any formula because it is a variable losses. Okay, let us have one example. Let us consider the earlier problem. Say a 80 kVA 1000/250 volt single phase 50 Hertz transformer has iron losses equal to 600 watt and copper losses equal to 400 watt when primary draws 50 ampere when primary draws a current of 50 ampere. Okay, so it is not a full load. It is not a full load. At this current, at this primary current, the copper loss is 400 watt. Okay, find, calculate first efficiency at full load and power factor 0.8 lacking. Second, efficiency at full load, okay, half load and power factor 1. Third, efficiency at full load and power factor 1. Okay, so this is given to you. Now we have to calculate solution. Primary full load current I1 equal to kVA into 10 raised to 3 divided by V1 equal to 80 into 10 raised to 3 divided by 1000 equal to 80 ampere. Okay, and we know that the copper loss varies as a square of load current, WCU proportional to IL square, load square. So WCU at FL, full load equal to, see, the losses at a certain load. What was that? See, for 50 ampere it is 400 watt. At 80 ampere what it will be, and that too varies as a square of load current. So 80 divided by 50 bracket square multiplied by 400. This will be the full load copper loss. And the WI is given to you. It is fixed or constant. Okay, so let us find out this one. See, 8 divided by 5 equal to square of this multiplied by 400. It is 1024 watt. Okay, so in this way we got the full load copper losses and the iron losses. So first, efficiency at full load and power factor 0.8 lacking. So efficiency equal to obvious percentage 80 into 10 raised to 3 into power factor 0.8 divided by 80 into 10 raised to 3 into 0.8 plus WCU 1024 plus iron losses multiplied by 100. So it is this much percent. Okay, so let us check it. 80 exponent 3 multiplied by 0.8 equal to multiplied by, so 64 exponent 3 plus 1024 plus 600 equal to, make it to inverse, multiplied by 80 exponent 3 multiplied by 0.8. So it is 97.52, 97.52%. Okay, multiplied by 100. Okay. Now see, let us calculate for the half load. So second one, efficiency at half load and a power factor equal to 1. Here x equal to 0.5. Okay, so efficiency equal to x into kVA into 10 raised to 3 into cos phi divided by x into kVA into 10 raised to 3 into cos phi plus x square WCU, remember, and WI is single, multiplied by 100. It is not varying. So x is 0.5 into 80 into 10 raised to 3 into 1. So 0.5 into 80 into 10 raised to 3 into 1 plus 0.5 square into 1024 plus 600 multiplied by 100 equal to, okay, percent. So it is nothing but 40 exponent 3. Okay, so 0.5 square multiplied by 1024, it is 256 plus 600 plus 40 exponent 3. Okay, make its inverse, multiplied by 40 exponent 3, 97.9, 97.90%. Okay, and the third one is efficiency at FL, full load, and power factor equal to 1. So without writing the formula, I would like to write directly. So it is 80 into 10 raised to 3 into 1 divided by 80 into 10 raised to 3 into 1 plus WCU 1024 because full load plus 600 multiplied by 100, and this is equal to this much percent. Okay, so let us check it. So 80 exponent 3 plus 1024 plus 600 equal to, make its inverse, multiplied by 80 exponent 3 multiplied by 1. So it is 98.01%. See, the efficiency of the transformer becomes maximum. You will get maximum efficiency at a power factor 1. You can calculate, see, I have calculated for the efficiency full load and power factor 0.8. Then you can calculate for 0.9. Now we have calculated for 1. You can calculate for 0.7 and draw the curve. Now it is observed that efficiency becomes maximum. The transformer efficiency becomes maximum at a power factor of unity. Okay. So in this lecture we have learned the losses in the transformer, efficiency formula, how the copper losses varies with the load current, or square of the load current, and the one numerical based on efficiency of the transformer. We will stop here. Thank you very much.